So let me zoom ahead and there. I don't like to have elasticity on the board when I'm saying something about energy. Okay, so here is the preview of what we're starting properly next time. Here are a couple of answers to homework questions along the way. What's energy? Energy is very important for Newtonian mechanics. That is to say, the topic of 111, talking about motion and force and energy that all goes together. We'll solve problems. We'll talk about energy in physical, in the sorts of systems that we've been talking about, ropes and pulleys and planets and tables and pushes and stuff. That energy ties in perfectly with that. Yeah, great, good. Energy is everywhere in all of your classes. Do you guys ever in your other classes talk about newtons? Really? No, really, do you? No? No, you were just nodding along as you understand what I'm saying. Do you talk about joules and calories? Yeah, right. Energy is hugely important in other areas. The force that one adenosine triphosphate molecule exerts on, wait, what does ATP bind with? Oh, come on, this should be a test question. What does ATP bind with? I don't know. Help me out. What does ATP do? Adenosine triphosphate? No? Look, even if even I know what ATP is, you guys should be experts on this by now, right? If a molecule exerts a force on another molecule, forces inside an atomic level with test tubes, it's really not a very efficient way to talk about things because it's very, 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 very difficult. Even Ant-Man finds it difficult to get down that small and measure things with spring scales. However, energy is everywhere, baby. It is much more applicable to chemical systems, to biological systems, to understanding the flow of physics from place to place and form to form. So, energy is foundationally fundamentally useful, and it's also, there's another thing that it's incredibly important for, and that is selling bullshit to tourists. If you go to Sedona, there are lots of adorable little shops that I frankly do like to visit, but you will see lots of little advertising blurbs on the crystals that they sell you, and they will talk about how this gives you, that gives you, this takes away energies of this form, that form, and the other form. I do want to make a distinction here as a metaphor for emotion, for spirituality. As a metaphor, I'm fine with it. But I do want you to know there is an acid test for whether something is physics energy, that is to say something that is connected in any way, shape, with the observable scientific world. And that is, there are a number of ways to put this, but the way I'm going to teach you is if it is conceivably possible to get it to lift a brick, it's physics energy. Otherwise, somebody's trying to sell you something. Huh? A brick. To lift a brick. If you could use it to pick something up, to lift a rock. It's conceivable to do that. It's physics energy. Otherwise, it's nonsense. But might be a useful, powerful, important metaphor for something, but it's not physics energy. So, for instance, a form of physics energy is thermal energy. Hot stuff has more than cold stuff. Here's how you could use heat to lift a brick. I use heat to boil water. I use water to spin a turbine. I use the turbine to, when I spin a turbine, it generates electricity. Use the electricity to power an electric motor to lift a brick. Bam, done. Or I could talk about light. Light has energy. Here's how I could use light to lift a brick. I use light to feed some plants, to make them grow, to have a cow eat them, and then I capture the cow's farts and light the methane on fire and explode the brick up into the air. Bam! There you go. Or I guess you could just use a solar panel and then go directly into the electric motor stage, but that's less silly. What other form of energy? Motion is a form of energy. If I have a moving car that is zooming that away, all I have to do is put the brick next to a ramp. The car smacks into the brick ricochets up the ramp into the air, the brick is lifted. Bam. Artistic style is not energy. It might be very important for the humanities, my friends, but not even the greatest or worst painting in the world, although it might elevate the human spirit, cannot elevate a brick. So, when you are seeing forms of energy in the world around you, look for this. There are billions of forms of energy, but there are also billions of people trying to sell you things. And you can tell if it's science or pseudoscience, if it is conceivable, if it is possible, if it is measurably possible to lift a brick with it. There's more than one way you can put this test. It doesn't have to be lifting a brick, but that's how I'm going to run this. That's my rule of thumb. We're not going to talk about all the forms of energy because there are more forms of energy than even I know. I probably can list a dozen, but I'm sure there's more than that. One of the problems with forms of energy, knowing what is energy and being able to define energy in an all-inclusive way, is that more keep being discovered. There are new forms of energy that get discovered periodically. We thought some time ago, we thought we knew everything there was to know about energy, all the different forms of energy. Then this lady found this rock that, hold on, heat is a form of energy, and this rock doesn't cool down. This rock just stays hot. What the what? And then she got cancer and died, and it was Madame Curie because she found radioactivity. What was going on inside the rock? Thermal energy was being created as radioactive energy was being destroyed. Ultimately, incidentally, E equals mc squared energy was being destroyed. The rock weighed an infinitesimally amount less, and that destroyed mass created energy. E equals mc squared is a cool law. Then we discovered, hey, look, there's a different form of energy that we didn't know about. We learned that matter itself is a form of energy, and inside the nucleus, crazy things keep happening. What else? In astronomy, new form of energy is currently, there is a known unknown called dark energy, which is not dark matter. Dark energy is a known unknown in that we can observe that there is something pushing on the fabric of space-time, but it is not behaving like other forms of energy. According to our current best understanding of the universe, all other energies try to contract things, try to pull things, try to exert, I guess, negative pressure, pulling things towards themselves, gravitationally, if you will. Dark energy is the one and only unknown form that pushes apart, pushes matter and space-time, pushes space-time away from itself. So there's a known unknown. Who knows? Maybe it'll be discovered. Maybe it will be understood in our lifetimes, maybe not. Sometimes it takes a long time. There are lots and lots of forms of energy. I'm going to give two generic words here that I want you to know. Transform means that energy changes its form. Well, that's pretty simple. If energy is changing from one form to the other, that is a transformation. The other word I want you to know is transfer. Transfer means energy goes from one object to another. As far as we can tell, if you have a closed system, that is to say, if you have a set of objects that are interacting with each other but not outside, there are no external forces acting on the collection of objects. The collection of objects, you might have energy change forms, or you might have the energy change objects, but the total amount of energy of all the objects and all the forms has to add up to the same, never changes. This is called the conservation of energy law. Yeah. We could do both. We could absolutely do both. For instance, I could heat the hell out of a thing of water and the water would boil, thermal energy goes pop, the lid on the stove lifts up into the air as steam pushes it up. So you could absolutely have heat energy that ultimately that heat energy from the boiling water goes into motion energy of the pot lid. You could have both happen. So transform, change forms, transfer, change objects. big principle, conservation of energy, says that the total amount of energy, if you add up all the different objects in the system having the energy and all the different forms that they have the energy in, the total can't change. Incidentally, I will admit to you this is a lie, as Madame Curie, posthumously, we realize, as I was mentioning earlier, follow the rabbit down its hole, and the form of energy that killed Madame Curie was, in fact, a form of mass turning into energy. Conservation of mass, conservation of energy. These chemistry laws, they're not actually real. There's one law called conservation of mass energy. You have to go deeper into physics to understand how. But I will say that breaking conservation of energy, conservation of mass separately, having to combine them, that only happens in, for us, relatively rare circumstances. It happens in radioactivity. It happens in nuclear fusion and fission. It happens in particle accelerators. So unless you're a particle physicist or inside a nuclear reactor or a bomb, or you're particularly doing chemistry of radioactivity, then you don't need to care about this. In all of the circumstances, matter stays matter, energy stays energy, and the total amount does not change. Okay, great. So that's deep, fundamental, powerful principles of energy. We're going to go rather more into what do they count? 4? I think 4 forms of them. Learn to calculate their amounts and use how to predict what happens in this circumstance, that circumstance, and the other circumstance without using force and motion laws. We'll actually analyze many of the same scenarios that we did with force and motion in the first, 2/3 of the semester without doing those laws, which is wonderful because then you don't have to remember them. And when the final comes around, I don't need to, I don't care to, I don't want to know which technique you used. If you're able to solve a problem, it doesn't matter which style you use to analyze it. So I'm giving you a way to cheat on your exam. Cheat on your exam. Okay, so having said all that, that's my 15 minutes on energy, the intro. Now let's spend 20 minutes on energy, on springs, and let's get out of here. Please note, if you downloaded these slides earlier today, there was a typo. I'm a big silly, and I can't fractions. I fixed it. If you re-download them, they're fixed. This version that I'm about to show you, the typo is gone. Okay, so here's half of the equations for today. F equals negative k delta x. Let's talk about these letters. F, or Fs. I ran out of letters. I didn't want to say S for spring force. That sounds silly. So I said Fs, force exerted by a spring, Fs. Force exerted by a spring is negative k times delta x. K is a constant. Any spring has a given k value. The constant for the spring is called, and you'll never believe this, very creative name, the spring constant. The spring constant multiplies the amount by which the spring is compressed or extended, the change in length. Delta x is how much longer is the spring than it was when you start. I should be precise. How much longer is the spring than its equilibrium, than its unstretched length? Note, if you stretch a spring, if it is longer than its original length, that's a positive extension. If a spring is 10 centimeters unstretched, now it's 11 centimeters, what would delta x be? Google form. If I have a 10 centimeter stretch, if I have a 10 centimeter spring that I pull until it's 11 centimeters, what's delta x? Google A. Meter? Negative? Hold on, cowboys. I'm asking for a number here. I have a 10 centimeter spring. I expand the spring by pulling on it. It is now 11 centimeters. What is delta x in this example? What is the change in its length? and defining delta x to be the extension beyond its original length. Yes, 1 centimeter or 0.01 meters. Now, if I want to have a consistent definition that delta x is the extension beyond its original length, now suppose I squeeze it, and now it's 9 centimeters. Google form B, what's delta x now? So the 10 centimeter spring has now been crunched to be 9 centimeters. If I maintain a consistent definition, what is the change in its length? Again, the traditional letter to use here is X, but maybe I should say L. Yeah, let's see. I've got 2s, I've got 1s, I've got -1s. But the vast majority of you see that the answer is -1 centimeter is correct. A 10 centimeter spring, which is currently 9 centimeters long, the change in length from its equilibrium is -1. Yeah? Okay. So, question. You can, but if I want to talk about direction, if I make this the displacement vector, then you can talk about the amount is 1 centimeter and the direction is negative. Okay, but the pointio I do have here is that the direction of the expansion or compression, positive or negative, and the direction of the force are opposites. Big shocker, if you pull a spring, it wants to compress, right? If you push a spring, it wants to expand, right? That's the minus sign. If I've got an extended spring, delta x is positive, then the force is in the opposite direction. The force would be in the negative direction. If delta x is negative, if I have a compressed spring, negative times negative is forces the expandy direction. My point for saying all of this is that it is muy common, very, very common for students to throw that minus sign in left, right, and center because you memorize it as an equation, F equals negative k delta x, and then don't think about what the minus sign means. The minus sign is the direction of the spring force. If you know that a spring is pulling you upward, you can just say that the magnitude of the force is F equals kx. K delta x, where delta x is whatever amount the spring is stretched by. You don't have to include the minus if you already know the direction. Much later, next semester in particular, we will discuss this again, and we'll be discussing how the minus sign here makes a world of difference when it comes to the difference between sine waves and negative sine waves, cosine waves and negative cosine waves. This minus sign actually explains stuff in the deeper theory. But I want you to go back to where this comes from. The minus sign just shows you that the direction of stretch and compression is the opposite of the direction of the force that the spring will exert. Stretch springs compress themselves. Compressed springs try to re-expand themselves. Don't plug in the minus if you already can figure out which way the stretch is. Great. Make sense? By the way, slinkies are not the mental picture I want you to have for a spring. Think of this kind of spring, ballpoint pen spring, right? This is what's in a ballpoint pen, right? Right? Yeah. The lengths aren't touching. You can pull the spring apart, duh, right? You could also push them closer together. Once the links, the turns, the wire starts touching itself, then the spring force is going to be very different. Once I've completely collapsed it, then it's no longer going to obey this equation. Right? We're never going to deal with, I'm never going to give you a problem. You will never have to deal with a situation where You have to calculate, do the spring links touch themselves? Well, now we've got a different situation. We're always going to assume that the spring is not stretched or compressed so much that the links are touching. And you will never have a problem where you are trying to compress an already collapsed spring. There's another thing that we're not going to do, and that is we're not going to overstretch springs. Well, inevitably in lab, somebody will overstretch a spring. Overstretching is actually a very important part of understanding springs and elasticity. The elastic limit, we're going to discuss that in a little bit. Springs, twists of metal, great, right? Love springs, they're everywhere. No, really, they're actually everywhere. What's a spring? A spring is a lot more than just little twisted pieces of metal. Sure, metal springs are springs. You can model F equals negative kx for pieces of twisted metal, sure. Guitar strings are springs. Rubber bands are springs, although those only really act in the expansion direction. You can't really compress a rubber band, it just folds. Tables are springs. Bones are springs. Now, some of these springs, if you try to compress them or stretch them by more than like this much, they're not going to act like springs anymore. If I try to compress this tabletop by more than a couple of millimeters, one, facilities is going to get me fired, and two, it's going to break. Actually, it'll happen in the reverse order. But if you look at carefully at the top of the table, don't tell my wife I'm doing this. If you look at the top of the table, as I jump up and down, the top of the table is in fact going up and down. It's a spring. Moreover, if I had three of you, hey, when is you three? No. That'll get me fired for sure. If 3 or 4 people were standing up here, would the table not deflect further down? The more force we applied to it, the more it's being pushed down, the more deflection it has. That's a spring, baby. Bones. I have been told, though I'm not that kind of doctor, I have been told that medical doctors you can actually use a test to find out something about bone health based on how springy the bone is. Now for this, they don't actually make your bone stretch and expand that much. Ouch. Also, malpractice lawsuit. But there is some degree of stretch or compression that can be done safely and presumably not very painfully that can allow you to determine, do you have osteoporosis yet? Or ever, or whatever. So anything that tries to return to its original size and shape can be modeled as a spring. And some things are better at this than others. That is to say, some things, the range of lengths that this still applies for makes more sense than others. Molecules, individual molecules. You can treat two, a hydrogen molecule, H2, if you pull those two protons a little bit further apart, there is a force pulling them back together. That's ultimately an electron bond, a covalent bond, right? Covalent bond? Covalent bond going on there. The electrical quantum mechanical forces, there's not an actual spring, but you can understand, you can start to analyze the system. If you say a little bit of displacement generates a little bit of force, what is the actual bond length inside this molecule? You can start to understand that by applying a spring model. So my point is, springs are really everywhere, and we're going to be talking about springiness of lots of materials, not just metal coils. That's a lot of talking. Thank you for your patience. Let's do a problem. Google Form C. Throw yourself at this. Flash. What's flash? . Blast it. Units, by the way, what am I talking about here? How far questions are not masses. Go back to the equations, my dudes. You want to know how far? What equation? What variable are you looking for? Did I remember to hit? Oh, thank God. I'll give you a hint. Without anything else said, if I say a spring stretches when a block is hung from it, you can imagine that the block is just sitting there. So there are two forces on the block. mg down, kx up. It is. It depends on the spring. And you can find it based on what's given. It is not a universal constant like pi or g or whatever. Okay, so here's how I would tackle this. Again, I hope that it is bleedingly not difficult to imagine that if something is hanging from a spring, the spring is stretched longer, the force that that spring will exert is upward. That is to say, the stretch direction longer exerts an upward force. I already know the force is upward. I don't also need to include a minus sign when I'm talking about the fact, when I'm talking about the direction. The more a spring is stretched, the further, the longer it is. That might be a positive stretch amount, but I can say I don't need to double count the negative kx when I already know that the direction is upward. I just included a positive kx and said that the amount that the spring pulls up must balance the amount that the planet pulls down. Are you okay with those signs being as they are? I mean, hell, weight is downward, right? Why did I say positive mg? Because I know that there's one force downward, mg, there's one force upward of magnitude k delta x. They must be balanced. I don't need to include their minus sign, the minus signs if I'm saying that two things are balancing each other. They must. They must. The magnitudes must be equal if two things balance to zero. Okay, so if you're okay with me leaving the minus sign out here, I mean, if you're okay with the minus sign not applying here, I could just say 0.3 kilograms times 9.8 newtons per kilo equals unknown constant times 4.04 meters of stretch. This allows us to deduce that K equals what? 73.5? The units for K, I said this on the previous slide, but I didn't say them out loud, I'm saying them now. Spring constant is newtons per meter. Spring constant is measured in newtons per meter. Great. I have applied this and discovered something about the spring. Now, how does the spring constant change when I do anything? It doesn't. It's constant. We have found the spring constant, which is constant. So now I could say, what happens if I apply a new force? When I apply a new force, the spring constant is constant, so I can find the new amount of stretch. Ten point something, 11 centimeters. Yeah, there are many correct ways. How'd you do it? Thank you for thank you for exactly leading into the next slide, which leads perfectly to the next point. If you know that force divided by stretch is a constant, F equals kx, so F over x is k, we are saying that the ratio, how much something is pulled to how much longer it gets, is a constant. We can set this up as a proportion problem. F1 over x1 equals F2 over x2 equals F3 over x3 equals blah, 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 over blah, 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 blah. Let's write this down. And let's shuffle this a little bit. I only have two examples here, but you could do this for any number. Anytime you have that F is directly proportional to some other quantity, if something is something times something else, if you have a simple multiple, then if you increase F by some factor, X must increase by the same factor. Here's the math. F over X equals F over X. I can rewrite this as F1 over F2 equals delta X1 over delta X2. Exactly as Jane intuited, if F increases by some factor, F over F is a ratio, X must change by the same ratio. We will spend a bunch of time next semester. I consider it one of my most sacred duties. Well, no, not really. But I consider it actually a real serious, practical, real-world gift that I can give you to force you to think about reasoning without just plugging into a calculator, but reasoning about the structure of a relationship, proportional reasoning. If F doubles, what does X do? It doubles. If F becomes twice as great, then X must become twice as great. If F triples, what must X do? It must triple. Whatever happens to F will happen to X because they are directly proportional. Whatever ratio happens to F, that same ratio will happen to X. Next semester, we will have like 5 different forms of that. We'll have as F doubles, X halves, as F doubles, X quarters, as F doubles, X stays the same, as F doubles, X quadruples. We'll have various combinations of what affects what. For this, since F is, as we say, directly proportional to delta X, whatever you do to F, delta X will change in the same proportion. Now, if you want to find K and plug in, as I demonstrated the first pass around, sure, do it. If you find spring constant once, then you can use it again and again. You can even use spring constant when I don't ask you about it. Just don't tell anyone, okay? If you're calculating spring constants, just for funsies, that's probably something you shouldn't admit to your friends. Alternately, as Jane was intuiting, as I did that follow-up, you could use proportional reasoning. If this is directly proportional to that, directly proportional means is a constant multiplied by whatever happens to X, changes F by the same ratio, and vice versa. Okay, I'm going to skip this problem because it's boring. For now, we'll come back. Maybe. Depends on how you all feel. Okay, so as I was hinting, as I mentioned briefly in passing earlier, if you stretch a spring beyond its so-called elastic limit, I had forgotten this term earlier, in the 3 o'clock class, someone asked me about it, blanked out on it, and then, hey, look, it's in the slides. Oh, I'm so smart. The elastic limit is the point beyond which a spring will not return to its original form. That's where Hooke breaks down. Hooke's law stops applying at the elastic limit. Beyond the elastic limit is not immediate breakage. You don't fracture just because you're deformed. I mean, I haven't fractured, and yet people tell me I'm deformed all the time. If you keep stretching beyond the so-called plastic region, you reach something which, if I recall correctly, is called the ultimate strength or ultimate limit or ultimate something. I'm not testing on this one. I don't remember this one. Then you'll reach a point where the material breaks or fractures. Again, I want to emphasize there's the elastic region, the plastic region, and the fracture point. We're never going to apply Hooke's law, Kx, when the spring isn't returning to its original shape. That's beyond the point it reaches. So far, so easy peasy. One equation. Okay, well, the second one is really hard. Just kidding. It's actually the same equation in a different form. Okay, Merry Christmas. F equals kx. What makes k? What makes a spring constant? Well, as I admitted to your classmate over there, spring constant isn't a true constant of nature like g or pi or e or whatever. Spring constant depends on the spring. If you got a given spring and you don't stretch it past its elastic limit, then it's going to stay k. But spring constant ultimately depends on the size, shape, and material of the spring. As it turns out, we can deduce the spring constant for simple situations if you know the size and shape and material of a spring. And the material part, just knowing the material part, that's called Young's modulus. Young's modulus is a deeper idea of how springy is a given kind of material. How springy is it naturally? The springiness of rubber is intrinsically different than the springiness for titanium. If you have the same shape of a block of rubber and titanium and you push on them, the rubber is going to spring more, right? So independent of size, we can talk about the material constant K, Y, Young's modulus, just tabulate the sucker. Also, Young's modulus is very common to pop up on what? On MCAT. And what they give in MCAT is they write down Young's modulus equals stress over strain. Because stress and strain are both words that y'all should be very familiar with in college. Stress and strain are precisely defined. Stress and strain are material science words that refer to force and length and stretch and size and shape, and we're going to define them on the next slide. But I want to have this down when you're writing first about Young's modulus. Young's modulus equals stress over strain is something for the MCAT students out here. This is going to be something you memorize. Incidentally, stress and strain are measurable quantities themselves. We're not going to deal with them outside of springs, but could. You may see them in other contexts. Stress and strain, you could graph them. If I graphed a quantity with stress on one axis and strain on the other axis, what would y look like? How could I see y if I had, say, stress on the vertical axis and strain on the horizontal axis? This is slope. If I have a stress-strain graph, I'm going to show you one later. If you have a stress-strain graph, the fact that you've got a constant equals the ratio of the vertical quantity over the ratio of the horizontal quantity, you're looking at a slope. If you have a straight line slope, you've got a spring. If you don't have a straight line slope, that's not a spring. Here we go. Here are the defining terms for stress and strain. Stress, this is the Greek sigma and epsilon, by the way. Stress is defined as force per cross-section. Strain is defined as proportional change in length. That is to say, stress is how much force is applied divided by the cross-sectional area. Hey, guys, do you guys remember the area formulas? It's the area of a square. Square is not pi r squared. Google form! What's the area of a square? Google form, what's the area of a rectangle? Google form, what's the area of a circle? So D square E rectangle F circle. G triangle. Give me the area formulas. See that you remember stuff. Judo forms D E F. I can't remember what I asked you in the homework, but it'll be one of these for sure. Square, square of side length S, rectangle of height by width, circle of radius R, triangle of base and height. Do you know your area formulas? D, E, F, G. Squares, rectangles, circles, and triangles. Whoa. Give me the area. If you tell me 2 pi r, then go to jail, go directly to jail. Do not pass go and do not collect $200. So in the terms given is what you should answer. I said the square side length is S, the dimensions for the rectangular H and W, the radius of the circle is R, and the triangle is H by B, H high, B wide. So far so good. No. No. So far so mostly good. Y'all don't ever answer in the terms given, but whatever. No, even though I told you no. 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 Okay, so I'm glad I asked. Yes, Lucas, that's what I want to see if people know. And it looks like you guys got squares and rectangles great, but not the other two. So triangle is half base times height. 1/2 base times height. A fair number of you got that. But I see a lot, well, not a lot, but too many people do not remember area of a circle. You may remember cakes are square. Cakes are round, but pi are square. Okay, I'm going to assume this is something that you're supposed to know before you pass high school. I'm going to assume that this is a reminder here. And I'm going to treat it as given that you know this. This is not physics here. This is high school geometry. If you do not know this, please memorize this immediately. 2 pi r is the circumference, the distance around. Oh, wait, hold on. No, here's another thing that came up in the 3 o'clock class. Google question H. If I tell you that a circle has a diameter of 5 meters, what is its radius? Google form H, if I tell you a circle has a diameter of 5 meters, find its radius. Good. Okay. So you all know what diameter is. You all know what diameter is. Good. Most of you know what diameter is. Okay, let me define diameter here. A diameter for a circle is twice the radius. This is the diameter. This is the radius. Diameter is 1/2 of the radius. So if I give you the radius, you just take, if I give you the diameter, you just take half of it to find the radius. Okay? Again, I'm never going to tell you this on a test or ever again in the future. This is stuff you need to know by now. But if you've forgotten it, there you go. So there are our area formulas and defining terms for circles. Now, I have defined then strain. God damn it. I have defined stress is force per area, cross-sectional area. Strain is proportional change in length. Let me give an example. Suppose I've got a 20% off sale. What's that mean even? What does a 20% off sale mean? I think it means that you're spending 80% as much as you would have, which is already too much. God damn it. Ugh, stupid capitalism. I am saying that my strain is 80% or 0.8. There, that's it. That's how much is left. What am I talking about? 20% off? No, inflation. Everything is double what it used to be. What's the strain? Things are twice as much as they are. They are how much percent more than they were? 100% more, right? The change in cost divided by the cost is an increase of 100%. Is remember that 200% does not mean twice as much. 200% increase is not the same thing as twice as much. Yeah, right? Google form. If something was $50 and is now 100% more expensive than it was, what is its new cost? Again, something started as $50 and the price has increased by 100%. What is its new cost? I start with a good which started as $50 and it has increased by 100%. What is its new cost? I will write this down. Saying words is hard. What is this? H? What costs $50 nowadays? A gallon of milk? Just wait till you have a baby. My God, the way he drinks milk. Used to cost. I mean, maybe it costs 50 bottle caps then. Sure, a gallon of milk costs 50 bottle caps.
That's still expensive. I could buy like molds for less.
I missed Fallout. I want to play it again. Used to cost $50. The price increased by 100%. How much does it cost now? This is the origin, this is the essence of strain. All right, and let's see how many we got. Nope, 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 nope. Okay, percent increase. Here's how we calculate percent increase. $5,000 feels about right for price of milk these days, but again, that's just because I have a baby who drinks too much of it. Percent increase. First, you find the percent of something, and then you increase it by that much. 100% of $50 is how much? $50. If I increase something by $50, how much is it now? $100. 100% increase. No, this is, yep, this is I. Thank you. 100% increase. Thank you very much, online person. 100% increase means I take the percentage of something to find how much there is, then I add it to that again. What's a 0% more than $50? 50, right? If I increase by 0%, I have not increased at all. What's 100% more than $50? $100. What's 200% increase on $50. Suppose I take something which costs $70 and I drop the prices by 700%. How much does it cost now? Google form. The president recently said that insulin have come down 700%. And I want you to calculate what insulin costs now. Insulin used to cost $70 and it went down by 700%. Insulin used to cost $70 for a shot or something. If the president is correct, prices decreased by 700%. What does it cost now? Run the numbers, my friends. Use the same form that we just did. Take the percent of the original thing. If I decrease by 700%, we're going to subtract off the change. What's 100% of $70? 100% of any quantity is itself. So 100% of $70 is how much? $70, right? If I decrease the price of something by 100%, how much does it cost? Did you know that being diabetic now makes you money? According to the president, and who am I to say otherwise, you now earn $420 per shot of insulin that you buy. Apparently, I'm not diabetic. Maybe I should be. I could use the extra money. The correct answer here is negative $420, apparently, because I take $70 and I subtract 700% of that, and I get negative $420. Next week, we'll talk about vaccines. No, too depressing. Okay, so, percent difference, sales amount is the essence of strain. Strain is the ratio of change, not new length to old length, but change in length to old length. If I have changed from 5 centimeters to 10 centimeters, I've increased by what ratio? Google form, what is my strain if I go from 5 centimeters to 10 centimeters? K. My original length was 5 centimeters. My new length is 10 centimeters. Google form K, what is my strain? I'll write it out because words are hard. If L equals 5 centimeters and then L equals 10 centimeters, what's epsilon? Plug it into the formula if you are in doubt. Plug it into the formula that I've given you right here, the percentage change. The lower L is the initial, it is the unstretched, it is the starting, not always starting, you don't have to start unstretched. L is the equilibrium length. If I have a 5 centimeter spring, which is stretched to become 10 centimeters, the 5 centimeter spring was 5 centimeters. It's not always the initial, but it's the unstretched. If I have something that's 5 centimeters, then I stretch or expand it. Okay, so again, I have a 5 centimeter spring. I double its length, find epsilon. Hey, please, by the way, notice the units. What are the units of L? Divided by what are the units of delta L? Or what is 1 meter per meter? Is that centimeters? Is meters per meter meters? The square meters? What happens if you divide meters by meters? Unitless. Meters over meters is unitless. Epsilon is a pure number. One more time. If I have a 5 centimeter spring, which is stretched to become 10 centimeters long, plug into the formula, use the idea of percent change. We are finding the change in length and dividing that by the length, the original unstretched length. The correct answer is 1 here, and let's find out why. The meaning of this is the change in length. If I started at 5 and ended at 10, what's my change? 5. I've gone from 5 to 10. That's a change of 5 centimeters. Delta L equals 5 centimeters. Divided by L, what I stated before, L is 5. And 5/5 also goes by the name 1. This was harder than I expected. Let's give another example. Suppose I've got a 20 centimeter spring, which is 25 centimeters long. I start with a 20 centimeter spring. I then push on it. And then L is 25 centimeters. Can you find strain? This is L. Maybe we should talk about percent difference in lab or something. Don't you guys do percent difference all the time in chemistry labs? Percent change? Hey, plug into the equations, my dudes. This does not have to be as hard as it seems. Okay, here's how to solve this. The change in length, if I start at 20 and end at 25, delta L equals 5. 25 minus 5 is 5. If I divide delta L divided by L is 5/20. L is the unstretched length. 5/20 goes by the name 1/4 or 0.25. Not 0.8. Okay. Do not simply divide original by final or new by final or final by new. This is not L new divided by L old. It is change divided by original, okay? Change. Let's do an example here. No, hold on. Sorry, one more thing. I'm not going to do the algebra here, but I'm going to say that if you plug in the defining equations for stress and strain and algebra them, K is made up out of Y, A, and L, y'all, as follows. K is y'all, YA over L. Young's modulus times cross-sectional area divided by the unstretched length of the spring, the original length of the spring, the equilibrium length of the spring, the length of the spring if nothing were touching it length. That's how you could calculate K from first principles. Okay, let's do a problem. And then I'm going to come back to that. Whoa, answers. Don't look. Spoilers. In this, I'm going to ask you to use scientific notation if you are not great with dangling decimals all over the place. I am terrible with that. I hate counting decimals and moving them around. So I love scientific notation. There are going to be some very small numbers in here. Watch your units. Ready, set, go. Give this a shot.
I just put everything about one.
Whose main character is a spider?
Huh?
Whose main character? It's a video game?
Paul.
Did you say words?
I said Hollow Knight. It's a game. It's one of the main characters from mostly Orc Spider, or at least they're based off of
All Night Silk
Hollow
Song.
Knight.
Hollow Knight Silk Song. I'm gonna Google that while you guys are working. Wait, does it have pictures of orb spiders? Probably. Oh, okay, good. Say it one more time. What's the name of it? Hollow Knight. Oh, she's cute. Kawaii desu. Aw. Oh, but it doesn't use real physics. I'm so disappointed. Whoa. That's pretty darn cool. Please note carefully the words I'm giving you, by the way. Note what I'm telling you and what you need to find. Here my final answer, by the way. I'm specifically asking for a difference. You don't have to tell me a percent difference. You can just tell me a amount of stretch, a number of millimeters or centimeters or micrometers or whatever. Hint, if you get larger than the diameter of the Earth, you've done it wrong. I encourage you to think about what it means to be 10 to the 5 meters and how big that is. You know what, let me be picky here because part of this learning process is juggling big and small numbers. Everyone, you need to give me units with your answer too. The correct way to specify a unit and number is give me number, space, units. You can tell me any units you want. I'm not going to say you have to give me meters or micrometers or whatever, but then just say a raw number. Also notice I'm asking for a amount of stretch, a distance here. I'm not asking for the spring constant. You could find spring constant. It's not a bad idea to find spring constant, but it's not what I'm asking. I've plugged the individual steps in. I encourage you be able to do these unit conversions. I haven't dealt with scientific notation much before. Are you guys okay with scientific notation? Yeah. Where? 2 times 10 to the 9 is the same thing as what I gave, 0.2 10 to the 10. 10 to the 10 is a very common exponent for Young's moduli. That's what it's tabulated in terms of. But I converted so that everything was in straight scientific notation. Okie dokie. We are now done with everything but energy for the rest of the semester, and for my sake, I'm out of energy too. Hey, there we go. That was the pun I was looking for earlier. See you on Wednesday.
I gotta go back to. I should-
Oh, Gina. Thank you. Thank you. Yes. Lucas, it doesn't matter. And Gina, yes. Sure. I didn't see it, but yes, why not?
You actually